Now let's put a capacitor and a resistor and a battery together in a single circuit, and I'm going to put them in series right now. It's just one loop, so they each have to have the same current. The battery has high voltage on this side, low voltage on that side, so the current's going to be clockwise. When I close this switch right here, I'll allow current to flow. Current will flow so that it charges the left-hand side of the capacitor positive, and it charges the right-hand side of the capacitor negative. So at first, the battery will be adding energy. The capacitor will not be doing anything, and the voltage drop across the resistor will be big. After some charge flows, so that this is positively charged on the left-hand side of the capacitor and negatively charged on the right, then the voltage will go up still across the battery because it's still a battery, but the voltage is going to drop some across the capacitor. And that means the voltage drop across the resistor is going to get smaller because some of the voltage drops across the capacitor. As I charge this up even more voltage drops across the capacitor, and so less of it drops across the resistor. And eventually, when this capacitor is fully charged, it'll have the same voltage drop as the battery has voltage rise, and so the voltage drop across the resistor will be 0. Now, just look at this equation. If we know the voltage drop across the resistor is I times R. If that voltage drop is decreasing with time, then I times R must be decreasing with time. Now the resistance certainly isn't decreasing. That resistor is still sitting there. So what's going to go down with time is the current. So if I close this thing, I'll get a current, because there'll be a current through here because there's a voltage drop through here eventually. But as this charge builds up, the voltage rise across the battery will start to show up as a voltage drop across the capacitor, and the voltage drop across the resistor will get smaller and smaller and smaller until it's fully charged and the electrons stop flowing. Now, we wrote out this equation for one loop. Delta VAB is 0. Here's 0. There's a battery. I times R. Well, what is I? The current is the rate of charge flow through the resistor. But these resistors in series with the capacitor, so it's also the rate of charge flow through the capacitor. And the rate of charge flow, what's happening at the capacitor is that the charge is building up. So the rate of charge being delivered to the capacitor is just the time rate of change of the charge on the capacitor. And delta V across the capacitor is, of course, the charge of the capacitor divided by its capacitance. So if you write this equation right here, you see that there's a derivative of Q with respect to time, and you also have Q. You have both of those, and then you have a constant E battery. The resistance is a constant. The capacitance is a constant. So you have some constants. You have Q of the capacitor, which clearly depends on time since it's charging up. And you have the derivative, so this is a differential equation, and you can solve it, and you end up with the equation that looks like that. Is this what we expect? Well, at t equals 0, that exponential function is 1. So this is 0. So at t equals 0, when I first close the switch, no charge on the capacitance. When t gets larger and larger, this exponential gets smaller and smaller and smaller. So eventually, the charge on the capacitor is the capacitance times the voltage of the battery. So this explains what we saw. Okay, so now let's change the circuit. Let's take the battery out. So I take the battery out. In fact, the battery doesn't make any difference anymore. But I have a fully charged capacitor here. Now, I left the switch open. capacitor and a resistor in series. What's going to happen? Well, there's a voltage drop across this curve. This is the high voltage side. This on the right is the low voltage side of the capacitor. And I know that current will flow from the positive to the negative side once I close that switch. So there's a voltage rise due to the capacitor. If I go around this circuit after the switch is closed, current will be flowing this way, so there'll be a voltage drop across the resistor. So the equation, the zero is the same if I go around once. I don't have a battery anymore. Q capacitance over C is a positive now, so I get much the same equation except the battery's gone. So what's physically going on? When I close this switch, the capacitor pushes charge through here, but how hard it's pushing depends on its voltage. So the voltage rise across the capacitor is going to equal the voltage drop across the resistor. That's what energy conservation tells us. Now, when I close this switch, charge is going to flow. So the capacitor will become, the charge on the capacitor will become smaller. And so the voltage rise across the capacitor will become smaller. And that means the voltage drop across the resistor will become smaller. That means the current will become smaller. So as this thing discharges, the current goes down more and more and more because the thing causing the current, the voltage across the capacitor, is decreasing. So what I get is a current that's big at the beginning and then goes down and down and down as the capacitor discharges. It goes down exponentially, turns out.